Hi friends, welcome to the course on high voltage engineering. This course has been developed by myself. I'm Ravindra Arora and also uh, Dr. Bharat Singh Rajput at IIT Mandi, and we would be conducting something like 40 lectures, and I hope you have a good learning time. The goals of this subject uh, or this course is to apprise you about the fundamental of high voltage engineering. That involves classification of electric fields and techniques of field estimation, because the performance of any insulation depends very highly on the electric field configuration. Then we will investigate how uh, the three types of insulation systems, for example, gases, liquid, and solids, behave when subjected to high voltage. Because the insulation system is the base of electricity, and higher the voltage, we need stronger insulation system. Then when we develop a gadget in the factory, for example, circuit breakers, transformers, and gas insulated systems, we need to test our product before it goes to the fields and applied in the fields. So you need to generate much higher voltage than the rated voltage of the equipment to test it. And therefore, we will be devoting a number of lectures for generation of test voltages and also measurement of measurement techniques of the test voltages and performance of individual apparatus. I did not mention one of the type of insulation system which we also be talking about is the vacuum. Vacuum is one of the very good quality insulation. It is never a perfect or absolute vacuum, but under low pressures, it behaves in a very good way as an insulator, and it is utilized in the high voltage apparatus very wide. Let me talk about the course outline. As you can see on the slide, the course outlines will be electric fields and their numerical estimation, breakdown mechanisms in dielectrics, intrinsic and practical strength of the dielectrics, the arcs produced during the breakdowns, we'll be talking also about that, breakdown characteristics of gaseous, liquid, and solid dielectrics under different field conditions. As I mentioned, the behavior of the insulation system very strongly depends upon the electric field. Then we'll be talking about the development of breakdown, which begins with avalanche process, and then it grows into streamer and leader phenomena. We'll also be talking about solid, liquid, and gaseous dielectric getting aged over the time, and how does that affect their insulating properties? Gas insulated system, GIS, are very widely used, developed something around 50 years back, and where they are very widely used, and there's something very sophisticated system, and the complete substations are made out of gas insulated system. We'll be talking about that. You might have heard a lot the word corona. Actually, what is corona? We have been using in the term in high voltage engineering since right since the beginning. Corona, as we put it, is nothing but local or partial breakdown of gaseous dielectric at very sharp or at any electrode system. We'll be talking in detail. The word corona comes from the Greek language. Then, as I mentioned, we'll be also talking about the generation and measurement of high test voltages and high test currents. Then, to on and off, we'll be talking about the national and international standards. IEC, International Electrotechnical Commission, is an organization which has helped in standardization of the high voltage equipments and other electrical engineering products. We'll also be talking about some numerical examples on and off as applicable. The goal of this course for learning is, first thing is the fundamental technology in the subject of high voltage engineering. Again, it has been said that it is, as I mentioned, it is electric fields which affect the performance of dielectrics. So the electric fields have been systematically classified. We're talking about that, and the performance of the various types of dielectrics, including liquid, solid, gaseous, vacuum, and testing of the equipment. That is also said to be high voltage laboratory techniques. We'll begin with electric fields and their numerical estimation, then with the breakdown mechanisms, the breakdown characteristics under the different field conditions, that is uniform, weakly non-uniform, and extremely non-uniform field configuration. The beginning of the breakdown process with avalanche, streamer, and leader phenomenon, aging, then gas insulated systems, etc., as I mentioned. When we divide the number of lectures, let's talk about it right in our first lecture. Electric field classification and field strength, etc. will take 4 lectures. Gaseous dielectrics, which actually the maximum work in the world has been done on air as a dielectric. Later, when other gases like SF6 gas was introduced, a lot of work has been done on gaseous dielectrics like sulfur hexafluoride, that is SF6 gas. So we'll be talking about the behavior, performance of gaseous dielectrics in detail, and that will take about 9 lectures. Then We'll also be talking about the liquid and solid dielectrics after building a base with the gaseous dielectrics. So that will take 6 lectures. Then breakdown in liquid and solid dielectrics, characteristics, how they are measured. There are different techniques in case of solid and liquid dielectrics. That will take 4 lectures. Then we come to the laboratory techniques, that is the generation of high test voltages and high test currents also. 6 lectures. Then the measurement of the breakdown voltage, all types of breakdown voltages. That is, we'll be talking about AC, DC, impulse voltage of 2 types, lightning impulse and switching impulse. So the tests are performed with all these 4 types of voltages over on the gadgets, because at least 3 of these types of voltages every gadget undergoes through during its life. And the tests performed in the laboratory are known as non-destructive high voltage testing of the quality of the produce. This is non-destructive because in no way the test voltage should cause any damage to the insulation system. So that care is taken so that no damage is initiated in the electric system. So that is why it is called non-destructive testing. We'll also be talking about the insulation coordination and over voltage generation in the power system. That we call it to transient over voltages, that is switching over voltage, lightning over voltage because of the lightning strike. They cause generation of traveling waves, they cause generation of over voltages in the form of traveling waves, and the whole network must be protected from such over voltages, and that is a subject of insulation coordination. We'll be talking about that also. Then, of course, about the IEC, as I mentioned just now, is on and off referring our talk to the international specification system. Then there is continuous development in the high voltage products, and we'll be talking about that in 2 lectures, and also numerical lectures, maybe numerical lectures may not, we get time, otherwise on and off numericals will be solving in during the course itself. You need prerequisite to be able to understand, and the prerequisite is in our institute in IIT Mandi, EE303, the course on power systems, and this is going to be a 3-credit course with 40 to 42 lectures, and the students who can attend are the senior BTech students, MTech students, and also PhD students can take this course, which will help them in understanding the power system and the phenomenon of high voltage engineering in a better way. We have a number of textbooks which you can procure. For example, our latest book, both the authors of this course have published a book, Fundamentals of High Voltage Engineering in India by Wiley India in 2019. Then I have other books, one published High Voltage and Electrical Insulation Engineering, which I wrote along with my professor in Germany, Professor Mosch, which is published by IIT Press, USA in August 2011. Prior to that, in 1995, my first book along with my Professor Mosch, High Voltage Insulation Engineering, Behavior of Dielectrics, was published. And of course, the NPTEL web course on high voltage engineering was also developed by myself, and that is available on the site given here. In this lecture today, let me apprise you with some basic terminologies which we following on and off. I found often these terminologies are misinterpreted and not understood very correctly by the students. So we'll be devoting the rest of the time today with these terminologies. For example, electric charge. What is electric charge? I've listed here on the slide, as you can read, from various sources how electric charge is defined. For example, presence of an uncancelled excess of either positive or a negative subatomic particles or the positive protons and the negative electrons in a substance. It is also defined as free subatomic particles of a polarity positive or negative. Then you can read yourself. There are so many explanations given. Electric charge is at, as I put it, the electric charge is at rest in dielectrics or in insulating materials. It rests. However, when the electric charge comes in contact with the conductors, it becomes restless. So that is why the movement of charge, which is nothing but current, we take conductors. But electric charge rests in all insulating systems, for example, in air, on the clouds, on human being when they are not grounded. So, very typical phenomenon is with electric charge that it finds its ultimate peace only inside the earth, and that is why we call it the Mother Earth. Like any other waste, the Mother Earth absorbs the electrical waste also, because in a circuit the magnitude of the current does not change, but the magnitude of the potential drops. So the same magnitude of the current flows to the other electrode, and which is often ground. So that is directed towards the ground, that is grounded, and that charge, that is the magnitude of the current, flows to the ground, that is taken care by the earth to go when it is able to go inside the earth. Now, the charge, I would also like to say, how does it develop? When I just clap, the charge is developed. When I rub my clothes even with my bare hand, the charge is developed on my clothes and it rests on my body if it is if I'm insulated from the ground. You might have seen when you are sitting on a plastic chair or very often inside the car and you come out of the car and touch the handle, it gives you a shock because when you are sitting inside the car, there is some kind of a rubbing going on between your body and your clothes with the seat, and the charge is developed which rests on your body. You are well insulated from the ground, and when you touch it back, the charge is rests full on your body, but when you touch it back, any metallic part, the charge becomes restless and it is discharged there. So that is the discharge process, and also in the process I've explained the production of charge. The production of charge, you produce current in a machine, or by friction, a lot of charge is produced in the atmosphere. The cosmic ray irradiation also brings charge of the cosmos to the earth. So the charge is produced by various means continuously. UV radiation produces electric charge. That is the free electricity. Charge is nothing but the free electricity. So to get rid of charge is discharge, as I explained. Withdrawing or transference of an electric charge is also discharge. You can also say sudden movement of charge. Well, I like it very much. It's sudden movement of charge is discharge. The electric discharge process can be typically described by the following. That is, ionization is the process by which electric charge, hence potential, builds up, while discharge involves movement of charge, hence loss of potential. Ionization builds up potential on a body, while discharge tends to lose it. This is what typically happens on the clouds when they gain charge because of friction, movement. The charge builds up and they acquire more and more potential. And when potential increases, the breakdown process and which leads to the discharge of the charge built on the clouds. We'll talk about it in detail. Very well said is electric charge leads to equalization of the difference of electric potential built by the charge between any two bodies or the electrode. So electric discharge tries to equalize the potential. I think I said wrong. Electric discharge leads to equalization of the difference of electric potential built by the charge between two bodies. So the discharge process equalizes the potential, and that is also how the phenomenon of lightning takes place. Electric field, you must have learned. A quantitative description of the attraction or repulsion of one electric charge by another at any one potential, at any one point. Between the 2 points, you can say electric charges between the 2 points. That is the, you can say, the attraction or repulsion force that is that can be described as quantitative electric field. It is also described as a ratio of the force extended on a positive test charge placed at the point to the magnitude of the charge. So you can say again the force exerted by the two charges placed between 2 points. Placed at 2 points. Yeah. The source of electric field intensity is electric charge. That means when the charge is there, it gives you electric field. So we'll do later the classification of fields. Unlike the electric field, the magnetic field is the portion of space near magnetic body or current carrying body in which the forces from the body or current can be detected. So as you can distinguish, electric charge comes from the electric field comes from the electric charge, whereas the magnetic field builds up with the current carried by a body or a conductor. The region around a magnet within this could be a permanent magnet or an electromagnet, which the force of magnetism acts. That is also magnetic field. Any space or region in which magnetic forces are present, as the space or region in or around a piece of magnetized steel or in or around an electrical current. Once again, as you see, this is around electrical current. That means that magnetic field is built with the help of flow of magnetic current. So that is the basic difference, the current and between electric field and the magnetic field. Electric field is the result of electric charge. Magnetic field is the result of flow of current. Yeah, we have already talked about electrical insulation, which is also known as dielectric. Now you would wonder why two names. In fact, these are two names. Dielectric is nothing but electrical insulation. We'll come to it, why it has been talked about that, why electrical insulation have been given the name or the term dielectric. As the dielectric, that is, you can say, unbare substance that develops electricity under friction. That is electric. Pertaining to or consisting of or containing electric charge or electric current. That is the electric. Electricus produced from ampere. This is a very old definition by friction. That is given the name for electricity, or you can say charged with a capable of developing electricity. So these are very, very old definitions of an electric or electricity, you can say. Then the dielectric. Dielectric, you can split the word dia-electric, as you can see it here, dia-electric. And or you can say, when you interpret it in the common language, non-conductor of direct electric current. That means the substance, dielectric is the substance which does not allow passage of direct electric current. That is why dielectric. Insulating medium or substance, as we put it, are non-conductive, non-conductor through which the electricity is transmitted. And that is the electricity is not able to be transmitted through an insulating material. Or you can say also without conduction, which does not have substance, which does not have conduction. A non-conducting or insulating material, a material which admits electrostatic and magnetic lines of force but resists passages or passage of electric current. Lines of force do exist in the material, but the insulating material, non-conducting material, does not allow passage of the current. So this is the way dielectric has been defined. I would put it why dielectric has been termed to be dielectric. In fact, there is no insulating material which does not allow some passage of conduction of current. You would be knowing a capacitor has a charging current. What is the charging current? The charging current actually flows through the capacitor, and the capacitor is built out of insulating material. So there is always some current to charge the capacitor, and which continuously flows. The charging current flows continuously. So there is always some minimal conduction of current through the insulating material. So you can say, but the dielectrics literal meaning is which does not allow passage of current. So you can say that there is no dielectric which does not allow some passage of electric current. In another word, the literal meaning of dielectric which does not allow passage of current, there is no dielectric which is a dielectric. All dielectrics do allow some passage of current. Yeah, some more basic terminologies I would like to apprise you, which we would be using in our course over the time. Electrical breakdown. What do you mean by electrical breakdown? If you can read it. Under certain conditions, when you apply voltage to the insulating material or the dielectrics, it may not be able to sustain that voltage, and it gives up its insulating properties, and a rupture in the material takes place. That is nothing but a short circuit of the insulating material, or short circuit takes place through the insulating material. So you can say the failure of electrical insulation properties of insulating materials is known as breakdown. Breakdown, or you can say electrical breakdown of insulating material. The electrical breakdown of dielectrics can be distinguished between global and local breakdowns. Global breakdown when complete rupture of the insulating properties all through takes place. The complete rupture or failure of electrical insulation between two electrodes is described as electrical breakdown and is generally termed as electrical breakdown, as I mentioned, or simply breakdown. But the local breakdown, that is something very interesting to be understood. It may happen when you apply the voltage on the electrode, which is resting on some insulating material. The insulating material may lose its insulating properties locally near the electrode only, not all throughout. So that will be, and that can continue for over the time, for a long time. And that is nothing but a local breakdown. So as you can read it, the phenomenon of failure of insulating properties confined locally to a part of the total insulation system provided between two electrodes is known as local breakdown. You can also say that since it takes place partially in the material, not globally, it can be described as partial breakdown and abbreviated as PB in an electrical insulation. The healthy part of the dielectric continues to provide the electrical insulation between the two electrodes in spite of failure of the insulating properties in some limited portion of the material. The terminology used very widely so far for describing this phenomenon, as I explained, is known as partial discharge, PD, not PB, in the literature. Since the word discharge has several other meanings too, it is more appropriate to describe this phenomenon as partial breakdown. So there is a need to shift over to PB from PD in high voltage engineering. The phenomenon, this phenomenon of local breakdown or partial breakdown, it occur in any dielectric, may occur in any dielectric under adverse conditions. Adverse conditions could be when there is a weak point in the insulating material or at a position where the electric field intensity is very high, unlike in the neighborhood, etc. And like breakdown, the partial breakdown phenomenon is injurious to the dielectrics, but it may not lead to complete breakdown immediately. It may take place over when if it continues, the complete breakdown may take place over the time. Hence, it is most undesirable. The partial breakdown is most undesirable because it does weaken the total dielectric, and this phenomenon should be prevented. Yeah, very interesting word, corona, especially these days when I'm recording this lecture for you. What is corona? As I mentioned, It's a Greek word and taken from the Greek language. Origin in Latin it is known as crown or cornice or garland. It is also known as halo of white light seen around the black disk of moon in total eclipse of solar eclipse. It is also seen in total solar eclipse. Again, it has been termed as brush discharge of electricity, a circle of light made by the apparent convergence of the streamers or the Aurora borealis. We'll come to it. So many ways it has been described. And the gaseous envelope of the sun or a star, sun is also a star. So if you can admire this happening if you happen to be able to see the total solar eclipse is a completely dark circle and lights are emitted out of this dark circle, the solar lights, and that is also known as corona. In electrical engineering, how do we describe, how have we taken, to which phenomenon have we taken the word corona? We'll come to it, but when we have very high pointed electrode available, the field at the tip of the point is very high because of the sharpness of the electrode. And when we apply a voltage to this electrode, the field in the air achieved is very, very high. And the air starts losing its insulating properties at the tip of the electrode. Electric field exists only in the dielectrics because an electrode is an equipotential surface. Electric field unit is volts per meter, or take it kV per millimeter or kV per centimeter. That does not exist in metal. It exists only in the dielectric. So when the electric field intensity in a gaseous dielectric is very high, the gaseous dielectric begins to lose its insulating properties at the tip of the electrode where the field intensity is very high, and partial breakdown activity takes place. Partial breakdown activity in gaseous dielectrics also emits light, photon, and that light seen in the dark is known as corona. We've been producing corona on and off in our test, high voltage test laboratory. So the next terminology what we are going to, I would like to you to be well versed. The streamer is very often used. Once again, it is very easy to understand in gaseous dielectrics. As we put it, the streamer, the word streamer, if you look at the dictionary, it's known as a long, narrow strip of material used as a decoration or flag. The crepe paper strips we use very often for decoration purpose. Or any long, narrow, wavy strip resembling or suggesting a banner floating in the wind. That is a flag, simply a flag, that also is the similar form as streamer, we put it, or a ribbon attached at one end and floating or waving at the other column. Suppose you take a crepe paper, a strip, and you put it on the, you stick it on the fan, one end of it, and you put number of them on the fan and then rotate the fan. You will see the waves like coming out of the fan formed by this paper. So this kind of lights shooting in the Aurora, I'll come to Aurora next. That is, you can say, is nothing but the streamer. But in electrical engineering, what is streamer? In electrical engineering, the partial breakdown phenomenon in gaseous dielectrics at hemispherical rods, because it will have a larger surface or a spherical shaped electrode or any other similar shaped electrode, appear like a streamer. When you apply sufficient voltage, there will be partial breakdown taking place at several locations on the surface of a hemispherical rod, and we increase the voltage, and this partial breakdown will propagate towards the opposite electrode in the form of streamer, as I described. And this you can also say it is like a shower of discharge from the electrode. It's like a water shower coming out of the hemispherical or circular shape or spherical shape electrode that one should actually see in the high voltage laboratory. So here, as I was mentioning, Aurora. What is Aurora? Aurora is luminous atmospheric phenomenon, electrical phenomenon radiating from Earth's northern or southern magnetic poles. Color of sky at dawn or at sunrise, you can see. In Roman goddess of dawn, or dawn is the morning, also known as Aurora, a luminous phenomenon that consists of streamers of arches of light appearing in the upper atmosphere of a planet. Polar regions, that is the polar regions, and is caused by the emission of light from the atoms excited by electrons, accelerated along the planet's magnetic field lines. The sporadic radiant emission of the light from the upper atmosphere over middle and high latitudes. People travel very often to the North Pole region, the countries like Sweden and Finland, where you can actually see this phenomenon happening, Aurora. This takes place in the upper atmosphere, where the atmospheric pressure goes down. And when it is irradiated with cosmic rays coming from the space, the gas at low pressure acquires a plasma, a state of plasma, and that emits light. So Aurora is a very interesting phenomenon. It is electrical phenomenon, also a high voltage phenomenon. You have to, in laboratory, in a vessel, you can produce Aurora, but then you have to bring down the pressure to the required level of atmospheric air and apply the voltage, then you can also produce Aurora. We will be talking about it also in due course of time in our lectures, which we did produce in our laboratory in IIT Kanpur. So I thank you very much. As I mentioned, there are some references. You are most welcome to refer this literature as and when required. Thank you very much. See you tomorrow.